Good evening and welcome to our webinar. I'm Chris McLaughlin, Secretary, Ireland Network. I have a few housekeeping items to mention in advance of the webinar. If you have any questions, you can post them in the Q&A box below and I will pass them to Mike on your behalf at the end of his presentation. If you wish to receive a CPD certificate, you can click on the link in the chat box below and download it from there. And finally, this webinar will be recorded for later posting to our YouTube page. I will now pass to our chairperson, Aidan Langley. Aidan.
Thank you, Chris, and welcome to everyone who's attending this evening, both IET members members of Engineers Ireland and other attendees. Mike, who's giving the talk this evening, he's an engineer and he founded Climate Care, which was the world's first carbon trading business, and he sold it to JP Morgan. Following that, he was appointed energy advisor to the president of the Maldives, where his brief was to create the world's first fully renewable economy. He's currently an investor and director in a range of new technology companies working to solve climate change, and he holds various research fellowships in the universities of Oxford and Bath. His current interests centre on the challenges of deep decarbonisation of society and the transition to a negative carbon economy. Mike's ongoing work in the field of economics uses cases for ammonia both as a fuel for hard to decarbonise sectors of society and as the next global fuel reserve to replace oil and gas. So Mike, I'd like to invite you to proceed with your presentation there, please.
Hello everyone. Is that up now? Can you see it?
That's fine, yes, I can see that.
Good. Right, let's move it to a slideshow. There we are. So lovely to have everyone here. And it's a very strange thing, isn't it, talking to an audience that you can't see. It's a bit odd, but it's taken a little while. I've got used to it now. What I want to do today is to challenge people about where they think aviation may go. You know, we've heard a lot about batteries, we've heard a lot about hydrogen, we've heard something about synthetic fuels, and I want to throw all of those into the pot and look at the question again and see whether we think perhaps we might have been missing something important. So ammonia is an aviation fuel. We've got 4 questions we need to answer. The first is it desirable? Do we actually want it? Is it possible? Is it affordable? And then finally, and probably the most difficult of those, is it safe? So what I'm going to try and do in the next few minutes is to talk through each of those pieces in that order. So let's start with, is ammonia desirable? So what possible energy vectors have we got? Batteries. So future batteries will get better than they are today, but this is a graph showing on the x-axis the gravimetric energy density of various ways of powering your aeroplane, and on the y-axis the volumetric energy density. Note they're both log scales, and batteries are right down at the bottom left-hand corner. Not a really good place to be. Hydrogen. Well, hydrogen is incredibly good in gravimetric terms. You know, it's right off the right-hand side of my graph there. Much better than kerosene up at the top right. The problem with hydrogen is that you're fighting with physics to use it. So the US government has got a target for practical storage of hydrogen, which takes you right down to that solid blue dot there. And the reason is that to have liquid hydrogen, you need to be operating at minus 253, about 20 Kelvin. Alternatively, you have to pressurize to 700 or 800 bar. But even if you have it as a liquid, it's interesting to note that there is almost twice as much hydrogen in a liter of liquid ammonia as there is in a liter of liquid hydrogen. Hydrogen superficially looks very interesting, but it's not really going to solve many problems for long-range flight. So that leaves us then with Biofuels E-Fuels. These biofuels are made from bits of plant, oils. E-fuels would be made from carbon dioxide, which you then chemically reduce and combine with hydrogen to produce a bit of chain elongation to produce fuels that you can use as drop-ins as a replacement for kerosene. Looks good, very interesting, but let's just look at what the world might look like by 2040, 2050, when these become the normal way of flying. The graph on the right, some of you might have seen, it is from the summary for policymakers of the IPCC's special report on holding temperature rise to 1.5 degrees centigrade above background. 1.5 degrees is tougher than the Paris target of 2. It is probably in its own right already too high, but as one famous British government chief scientist said when questioned why he wasn't making these points to politicians, he said, if we said how difficult it was going to be, no one would believe us and they wouldn't do anything. The blue region there gives you an idea of where we might need to be with no or limited overshoot in our budget. There'll be a bit of overshoot. The gray is what we might have to do if we have more realistic amounts of overshoot. And if you look at that, you can see that somewhere like 10 gigatons a year of negative carbon dioxide is what we're going to need sustainably, possibly for 100 to 200 years. This is not net zero, guys. Don't be fooled by the comments about, oh, we're going to get to net zero. No, 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 we have to get to net negative. And when you're at net negative, there is no carbon coming from convenient flues or anything like that. If you're going to get to net negative at 10 gigatons a year, because CO2 is so dilute in the atmosphere, you have to treat something like 30 million tons a minute of air. This is a vast, vast exercise. It will consume something like 25% of the world's current primary energy supplies just to do that. This is going to be pretty challenging. Now, in that context, imagine that you're going to capture some of your CO2 and turn it into fuels and re-emit it. Well, every ton of fuel emits 3 tons of CO2. Business as usual emissions suggest that by 2050, we'll be at 2 to 4 billion tons a year of CO2 from aviation. And that adds 20 to 40% to an almost impossible global CO2 capture needs. This is not likely to happen. Biofuels then are the next resort that people turn to and say, well, but can't we use biofuels? And of course you could use biofuels. You can make airplanes fly on biofuels with no problem at all. But we are already deforesting large parts of the world to feed us. To get a ton of biofuel, you need a ton of palm oil. There's your vegetable oils. That's the CO2 emissions that come from producing a kilo of them. If you want a ton of vegetable oil, it'll cost you 11 tons of CO2. Now that's a combination of direct emissions and indirect emissions, the opportunity cost of not reforesting those spaces. And in the case of oils, you've got lots of peat being lost in Kalimantan to provide the land for the palm plantations. And of course, you've got massive biodiversity loss. But then when you've got your ton, you've still got 3 tons of CO2 that you've got to dispose of. You can't just keep, you'll have to keep getting that back. So this leaves us with ammonia. Sorry. Ammonia is easily liquefied, 10 bar, minus 33 centigrade, which is the air temperature at 8,000 meters anyway. It's a natural liquid. It's very flexible. You can burn it, you can use it in fuel cells. It's not as good as kerosene, but the question is, could it be good enough? It's the best of all the other alternatives that we've looked at. And then, well, why ammonia? What about some other chemistry? Well, you can look around the periodic table. There aren't many other things that you could carry hydrogen with and use as an energy source. I mean, if you go down the periodic table, you end up with solids, silicon, for example, but silicon dioxide is not the kind of thing you want to carry around and be throwing out of an engine. It's sand. And ammonia is interesting. I mean, brown ammonia has been around for 100 years, a global industry. Green ammonia is totally sustainable in the long term. It's made from earth-abundant stuff, air, water, sunshine, no rare materials, no carbon. There's a huge existing market for it. Shipping will probably lead. Shipping is already moving towards ammonia. And, you can see there in the Second World War, the Germans took all the road fuel for their tanks in the Russian campaign. And so the Belgian municipal authorities in Brussels converted their entire bus fleet to run on ammonia. So is it possible? Well, let's just look at some 50-year shifts in aviation. That was 1903. That was 1953. That's what you can do in 50 years. By 2003, we were here. There's an amazing change again. But in civil aviation, in those 50 years, we added a few windows on the top deck of a 747. Of course, there was lots of work went on improving efficiency, engines improved, flight control systems improved, avionics improved, but fundamentally, the plane of 2019 was utterly recognizable as the plane of 1969. So my first thesis is that aviation actually could move faster. It needs the right stimulus. How would you adapt to ammonia? Well, there are some major challenges. The first of those is that ammonia has something like 40% of the energy content per kilogram of kerosene. And the big one is that ammonia brings safety concerns as a result of vapor toxicity. It's really toxic at a concentration somewhere above 3 to 3,500 parts per million in the air. So what are the fixes that we could put in place? Well, the first is we could move from jet to propeller. This increases your propulsive efficiency materially. It will slow the aeroplane down, and that might be a price we have to pay, though the use of ducted fans and contra-rotating propellers might give us quite a lot of that speed back. Though it often seems to me that actually the best way to speed up a journey would be to remove all the shopping from the airport. I'm sure that the 3-hour check-in time is there really to encourage you to buy things. We could move to fuel cells rather than combustion, and that would increase the thermodynamic efficiency hugely. And then on the safety side, and I'll talk about this a bit later in the talk, we can do some clever things with how we store fuel on the aeroplane. We can store it as very ultra cold liquids. We can possibly even store it as ice. And the prize is huge. We could have quieter, zero emissions aviation. It would become the most sustainable form of transport of all. It would move from pariah to prize. Very, very little land take, much less than rail or road, no intrusive noise, much faster than the alternatives. It's much safer than the alternatives. It's flexible and responsive. Once you've built a road or a railway from A to B, you can't really move it if patterns of travel change. And of course, it has unlimited growth potential. So if we're going to use ammonia, we've got two contrasting approaches that we can think about. One is combustion, and the other is fuel cells. So combustion is really a near-term solution. We've got existing manufacturers that know how to make turbines. I've written here, NOx control is not fully resolved. It's worth just talking a bit about this for a moment. The problem with ammonia in a combustion process is that when you strip the hydrogen off it to oxidize to water, you leave an ammonia free radical sitting unbonded, an ammonium, and sorry, what am I talking about? A nitrogen. And that sits there, and there's another nitrogen sitting nearby, and hey presto, you get N2 most of the time. But occasionally you get the N bonding with oxygen and giving you NOxes. And it's a much easier thing to happen than when you've got just N2 there and you have oxygen as well. That requires a very high temperature to form NOxes. You can get much more NOx formation at lower temperatures in combustion. The solution to that is being worked on at the moment. In Cardiff University, they're doing quite a lot of work on combustion. One of the really interesting things about ammonia is that ammonia itself is the cure to NOx, because if you put a bit of ammonia into the exhaust gas stream, it reduces the NOxes to nitrogen, and hey presto, you get NOx levels down well within regulatory limits. So the guys at Cardiff are down at sort of 100 ppm or thereabouts in gas turbine burners. That's quite interesting. You can get the efficiency up to about 37, 38%. What you do is you don't burn pure ammonia, you burn a mixture of hydrogen and ammonia. You break the ammonia down into ammonia and hydrogen, roughly 70-30 mix. But in the process of doing that, you use heat, and you can use the heat from the exhaust, and that gives you an increase in the amount of chemical energy, because the hydrogen picks it up and turns it into chemical energy. It's more expensive, combustion. Running gas turbines is an expensive business. Fuel cells are different. They're, in the longer term, they're going to be the solution. You need to rethink the complete aircraft system right through to airframe design. There are, of course, no NOx issues. Your solid oxide efficiency is up to somewhere like 70%, solid oxide fuel cells, and they'd be much less expensive to run in the long term. There are no moving parts. So what's the roadmap for ammonia power look like? So what I've modeled here is an A320 class aeroplane. I've taken the same maximum takeoff weight, the same payload. I've done nothing to change its aerodynamics, and there are improvements we can make there. I have made it fundamentally propeller driven. I've reduced the speed from about Mach 0.85 to about Mach 0.45. And I've modeled two different options, an ammonia turbine and a fuel cell electric. That plane on the right is one that I first flew in out to East Africa. It was a wonderful aeroplane, about 385, 400 knots, not a bad traveling speed, not as fast as today. So if we look at those four, at the different options for how we could power this, on the left here, you have a graph which is the comparative energy use, megawatt hours per 1,000 kilometers, for four different ways of propelling the aeroplane. With the existing turbofan, with an ammonia powered turboprop, with a 60% efficient fuel cell and a 70% efficient fuel cell. And the delivered energy at the bottom there, the blue bit, is exactly the same across all of them. And that's the energy that's put into moving the plane forwards. The propulsion losses drop considerably. That's the orange band as you move from turbofan to turboprop or electroprop. Your thermodynamic losses drop dramatically, and the electrical losses and the mechanical losses as you move away from a turbine. That's the gray area. And of course, the fuel cell losses sit there on the right-hand side with the fuel cells. So what you see is that in energy terms, fuel cells, 60-70% efficient, are dramatically better than kerosene in a turbofan. The graph on the right replicates the same things, but this time it's the comparative mass flow, looking at kilograms per kilometer flown. And you see the turbofan is the most efficient in terms of weight. The turboprop looks not very good, and the two fuel cells get better, at just 70% fuel cell efficiency, you're almost as good as the turbofan. And that's really interesting. Hydrogen would never get anywhere close to that. The problem that you have with flying, and I don't know how many of you are pilots, The problem that you have is takeoff and climb. In the cruise, you need a relatively small amount of energy, maybe 40% of the power that you need at takeoff. And that's convenient because your gas turbine's dealing with air that's only got 40% as much oxygen in it, and therefore the power curve matches roughly what you need at different phases of the flight. What you actually need if you're going to climb then at 2,000 feet a minute is a very, very substantial amount of extra power, perhaps 10 megawatts per engine compared to in the cruise. If, on the other hand, you're climbing at the slower rate of a turboprop, you only need to add something like 4 megawatts per engine. And this comes to one of the biggest problems with fuel cells, which is fuel cells are heavy. And so you want to size your fuel cell for the biggest part of the flight, which is the cruise. And that leaves you with the question of how the hell do you actually get to the cruise? How do you get in the air? And the solution to that is to have a hybrid and to put an auxiliary power unit and generator in there. And these are very light units, very high power to weight ratios. You can burn an ammonia hydrogen mix that's been cracked, and you could even burn biofuel E-Fuels. You need a very small quantity indeed. You only need it for the first 20 minutes of the flight. But let me just have a word, talk a bit about fuel cells for a moment. Basically, if you think of a fuel cell, it is fundamentally a linear device. Fuel comes in at one end and it flows through the cell, and on the way it is consumed, and at the outlet you have mostly consumed fuel. But of course, the rate of consumption will fall as the partial pressure of fuel falls. And if you have an infinitely long fuel cell, of course, you could use it all, but that would become incredibly heavy. So you have this problem, which is, do I build a fuel cell that consumes all of the fuel, or nearly all the fuel because it's asymptotic, or do I waste a little bit of fuel? If you want high power density fuel cells, one of the solutions may well be to run them slightly slightly less efficiently and waste more fuel. The beauty of this, though, is that we can now take the wasted fuel from that and put it into an auxiliary power unit and essentially burn it off and generate power with that too. So we have an interesting piece of engineering here to optimize the balance between the fuel cell and the gas turbine. There's also considerable exergy available to you at 600 to 800 degrees centigrade, and there's some heat recovery possibilities in there too. So what does this mean for the range of the aeroplane? On the x-axis, I have the power density of your fuel cell in kilowatts per kilogram. And on the y-axis, we have the range in kilometers. The dotted purple line at the top is the range of a Boeing 737 or an A320 today burning kerosene. If we converted that to a simple turboprop burning ammonia, it would be the brown line in the middle of the graph. So even if we take the simplest of choices, we can get realistically 3,000 and a bit more maybe kilometers of range out of burning ammonia. The fuel cell options are the two red lines, 60% and 70% efficiency. And you can see that as the power density rises above about 1 kilowatt per kilogram, you start to get really useful increases in range. And you can get up to 5,000 kilometers with high power density fuel cells. So the way that I see this happening is that we will start with turboprops running on ammonia. That will let us put infrastructure into airports. That will get the systems in place. It will allow us to play with safety systems and the like. In the interim period, people will be doing work on fuel cells, and they will come into their own maybe 5 to 10 years later. Can we afford it? So one of the things about ammonia is that ammonia is made in a number of ways. Today, brown ammonia is made by steam methane reforming to produce the hydrogen. In the future, it's going to have to be made with electrolysis, and it's going to have to come from renewable power. Solar power in sunny deserts is already about $13.50 a megawatt hour. Perovskite tandem cells due out from people like Oxford PV this year will be hitting 26% efficiencies, and I think they have a roadmap to go to 35% efficiencies. I can see solar cells producing power at well under $10 a megawatt hour in sunny places. I've assumed no improvements in the Haber-Bosch process. That's pretty mature and unlikely to change very much. And what we have here is the cost build up in dollars per megawatt hour of lower heating value. And you can see today, ammonia at $100 and something a megawatt hour is not a cheap fuel, but by 2030, 2040, it's a very, very competitive fuel. How competitive? Well, think about your aeroplane for a second and think about running it on either the turboprop or the two fuel cells. The graph at the bottom left there is just a reprise of the one you've already seen. The larger graph compares a 35% efficient kerosene turbine with a 60% efficient fuel cell propeller-driven plane. The red dotted line across the middle is the cost per megawatt hour of delivered energy. This is energy imparted to the airframe from the existing engines. And it's about $200 odd a megawatt hour. And that's at today's very depressed kerosene prices. The green dotted line is the same thing with $100 a ton of CO2 added. The three curves are for different costs of capital producing ammonia and burning it in the plane. And what you see, the 2020 is the purple one. 2020 is not very attractive today, and the fuel cells are probably not ready. But by 2030, the light blue, or 2040, the sort of orangey brown one, actually, the delivered energy cost of ammonia is cheaper than it is from kerosene. This is hugely important because fuel is the biggest single part of an airline's costs. So that takes me to the most challenging part of this. How safe is it? The first thing to say is that ammonia is non-flammable. It is almost impossible to light ammonia in open air. And both the UN and the US Department of Transport treat it as a non-flammable substance. The problem for ammonia is its vapor toxicity. It's lethal at 3,500 milligrams per cubic meter. And the last thing you want is people to be caught in that. So safety implications, well, on the ground, I don't think we have to worry. You know, we've got 100 years of experience in the midst of urban areas. It's a fairly negligible list. I think Los Angeles, there are 50,000 tons of ammonia in the docks. In Rotterdam, there's 30,000 tons of liquid ammonia in the middle of the city. The fire risk is dramatically reduced compared to kerosene. So let's just think about aviation. Well, if you have an accident at height with no survivors, ammonia clearly doesn't pose any additional risk because everyone's going to die anyway. And there are two kinds of accidents, therefore, that matter. There are survivable crashes, and there's a surprising number of survivable crashes. Airplane comes down. Classic one is a runway excursion. You know, it slides off the runway, it crashes over a bank, something happens, and some people survive. And the second type of accident is crashes into populated areas. And so the key questions are really, how large are the risks? Because let's be clear, nothing has no risk, and can they be mitigated? So I've looked at every single aircraft crash between 2000 and 2019, 20 years of data for every cargo plane and every passenger plane with more than 9 seats globally. And the graph shows you the crashes, blue line, and deaths, red line, per billion journeys. And it's per billion journeys, not per billion or 100 billion kilometers, because crashes tend to happen on landing and takeoff, not in midair. Regardless of the fuel, the risks are falling fast, and they will continue to do so. You know, we are moving into a world of much higher levels of artificial intelligence, much better control systems, much more reliable engines. We have aircraft that are in this crash register that are sort of 50, 60-year-old designs. If you're flying on ammonia, you will be flying a new design of aeroplane. I think that the risks in 20 years' time are going to be vanishingly small. But then when you look at the individual crashes, what you discover is that many of those crashes, there is no or very minimal fuel tank damage. So survivors are fundamentally not at risk. On the other hand, many crashes involve fires, which cause a major loss of life. So you probably gain more than you lose there. But let's not accept the gains. Let's just look at the losses. Simple projection of the data suggests that by 2040 to 2050, we will see 10 to 15 people's lives being put at risk per billion journeys. Your odds of being struck by lightning are 10 times as high. So I'm not sure, I mean, it is clearly a risk, and I'll talk about mitigating it, but actually it is not a material risk going forwards. This is the real problem. It's risks in urban crashes. They aren't reducing. If you look at the two numbers in the table at the top right, 2000, 2009, there were 9 such events, plus there were the 3 9/11 ones, which came to 12. 2010 to 2019, there were also 12. And why is that? Well, there seem to be several reasons, actually. The first is there's an increasing number of flights. So every airport sees just dramatically more flights. There's an increasing population close to airports, particularly in a lot of the developing world, where airports started quite a long way from centers of population, and population has moved closer and closer and closer. And there's a lot of aviation growth in countries with very poor governance and safety culture. So if you look at the pie chart on the right, start at the Republic of the Congo, the biggest slice on the right-hand side, most of those were actually old Russian cargo flights. Then the DRC, then Nigeria, then India, Pakistan, Iran, Indonesia, Venezuela, Georgia. Most of these are countries with very, very poor safety culture, very poor governance. And one would expect over the next 20 to 30 years, these things will change. And the scale of crash is also a lot less serious than it seems. 16 of the aircraft had less than 35 tons of fuel capacity when full, and half of them were over 40-year-old designs, and 12 of the crashes were on landing with low fuel. One of them didn't have any fuel on board at all. So only a very small proportion of those are material problems. Nonetheless, we have to look at how we mitigate them. So the big problem is going to be vapor. And in the 1940s, late 1940s, when helicopters were coming into the US military, the predecessors of NASA and the US civil aviation regulator looked at crashing planes into concrete blocks to see how they could mitigate fire risk. And what they discovered was that the big problem is that in an impact, you create a plume, and a plume of mist particles, tiny particles. The problem with tiny particles is the vapor pressure increases. And this makes life a bit difficult. If you've got kerosene, very low ignition energy required, and you get a flash fire. However, ammonia is very different to kerosene. At minus 77 degrees centigrade, which is its freezing point, and a long way above liquid nitrogen, which is a very easy thing to handle and is widely available, the evaporation rate is almost negligible in air. There isn't actually very much energy in air, if you think about it. You know, a cubic meter of air has only got a kilo of air in it, and its specific heat is not particularly high. The specific heat of ammonia is high, and the latent heat of vaporization is surprisingly high. It's quite difficult to get ammonia to evaporate. You get better evaporation if you follow the blue curve, which is at a 15-mile-an-hour wind than a 5-mile-an-hour wind. But of course, if you've got a 15-mile-an-hour wind, you will also have almost certainly much more turbulence. You'll have much greater dispersion. Once the ammonia has warmed somewhat, however, it's then lighter than air, and so it rises. So there's a lot of work to do here, but we do start with a position which is quite attractive. It needs, I say, it's going to need some experimental work. It's going to need some development, but I think we can do better than just taking a full tank of ammonia liquid anyway. So there are three different ways that we might consider mitigating these risks. The first is to adopt something that the military use already and have done for a long time, which is to fill the tanks with open cell foam and to have small compartments in them. Doesn't add much weight at all. And if you've ever taken a bath sponge out of the bath and put it on the side of the bath, it's surprising how much liquid it will hold for a very long time. We can reduce dramatically the rate of efflux of liquid ammonia from a crashed and broken open tank by filling it with a sponge. Of course, if you then surround the tank in a lightweight fiberglass or something like that as a coalescer, anyone who's a chemical engineer will know that there's a lot of work being done in looking at how to coalesce mists. You could dramatically reduce the amount of mist formed. So that's one of the things we can do. The second is really intriguing. And that is that we can pump ammonia in as a slush. If you pumped ammonia into the tank at, say, a 75% ice, 80% ice slush, and then bubbled some liquid nitrogen through, you would freeze it. You would actually have a solid block of fuel. And if you crash that, ice simply doesn't form mists. You can have some sort of loose fiberglass in there or something like that to hold the particles together. And then to get the ammonia out, you simply use liquid ammonia to scavenge the solid. And you've got plenty of heat around to do that with. And so basically you have a block of ice and you're taking your fuel off it only as fast as you need it. And the third, which is really intriguing, is to use rheology modifiers to make a sort of honey-like consistency. If anyone has used hand sanitizer recently, and I bet you all have, you squeeze it out and it comes out slightly thick, a little bit like runny honey. But what you've got largely is going to be alcohol, isopropyl or ethanol even, or not methanol usually. And they're classically very, very runny. What has been done is a small amount of a rheology modifier has been added, and it creates some hydrogen bonds that holds the thing together and makes it very, very difficult to make a mist from. Try making a mist from a jar of honey. It's not an easy thing to do. And what about the passengers? Well, I said that there weren't going to be many at risk. Surviving passengers will be closest to the highest concentrations of ammonia during an evacuation. But citric acid neutralizes ammonia very effectively, and the ammonium citrate's a safe food preservative. It's not a great problem if you have that. And you know, a filter mask like these with something like 75 grams of citric acid on would allow you something like 15 minutes of safe breathing at concentrations up to 40,000 milligrams per cubic meter. In all of my analysis of crashes, I didn't find a single life that was saved by a life jacket, and yet we've all had the drill which shows us how to wear it and how to put it on and where it is and so on. Actually, masks might be much more useful. So, environmental risks. These are material and we need to think about them. Ammonia is already disturbing the global nitrogen cycle. It's a major issue because it's a fertilizer, or it's the base of fertilizers, and it enters the water table and it enters the atmosphere. But the reason it's a problem is because we spray it all over the countryside. Other than rare gross leaks, ammonia as a fuel is nothing like a risk. I mean, it's not in this, it's orders of magnitude less of an issue, because the whole purpose of your ammonia distribution system is to contain it. And because ammonia is really easy to smell, very low concentrations can be easily detected by smell alone, and small persistent leaks are found. And I want to just mention NOx. NOx can be avoided with fuel cells. We can control it in combustion, either by adding traces of ammonia into the back end, or actually just cracking to hydrogen before combustion. You can't get it pure enough to use in certainly the current generation of PEM cells, but you can get it, use it in solid oxide fuel cells. And you have the great advantage that in the, cracking ammonia to hydrogen and nitrogen is endothermic. And so you can recover some of the exergy available in your exhaust gas and put it back into chemical energy in the form of hydrogen. So it's actually both an energy efficient, unusually for something that is a pollution remover, it adds to the energy available to you rather than subtracts it. So in summary, is it desirable? Yes. Ammonia is a rare, truly sustainable fuel made with earth-abundant elements, powered by sunshine. It is, think of ammonia as just liquid sunshine. Is it affordable? Well, I think it will be. I think green ammonia is going to be cheaper than biofuels, or, well, I know it's going to be cheaper than biofuels or e-fuels, and it's almost certainly going to be cheaper than kerosene today if you use it in a fuel cell. Is it possible? Yes. We're going to need to do some R&D. There's no question about that. We've got to think very hard about infrastructure and how we develop aviation and how we build our aeroplanes to suit the kinds of spaces and mass distributions that are going to be needed. But there's no fundamental physics or chemistry or engineering that says we can't do this. The numbers just work. Is it safe? Yes, it could be. New fuel tank design is going to be the heart of this, and increasing aviation safety just takes away a whole class of risks. So I would contend that ammonia-powered aviation could become the most sustainable form of transport, beating all of them, and actually moving aviation from the industry everyone loves to hate to the industry everyone loves. And that's it. Thank you very much.
Thanks very much, Mike, for an excellent presentation. I now have some questions to pass on to you. The first question, is ammonia included in the Sustainable Aviation Fuels bracket? And how can we motivate Rolls, GE, P&W to build engines in this way?
Dear attendee, are you from Rolls-Royce, GE or Pratt & Whitney, please? I have had indirect dialogue with Rolls. It's a challenge because their entire businesses are premised upon the kinds of things that they have spent billions and billions of dollars working on. And all of these businesses take where they are and they try to extrapolate forwards and say, how are we going to adapt to this world of sustainability? What they actually need to do is go to 2050 and extrapolate backwards. And those two lines don't always meet. So I think we're going to have a real problem with the incumbents. We have had the same thing happen in the motor industry, and Tesla has dragged them kicking and screaming into the world of sustainable transport. I'm not sure how we're going to do it, but it will happen, and it might just happen because the airframe manufacturers, the Airbuses and the Boeings, see this as an opportunity to grab a big piece of the industry that they otherwise don't get, which is making powertrains.
Thanks for that, Mike. There's another question. it hasn't come in by the Q&A box. Would there be any benefit in equipping airfields with catapults, a longer, slower version of an aircraft carrier type that would minimise power requirements for takeoff?
It's interesting. You could do, and I did look at this actually. I wouldn't use a catapult, but you'd use an electric dolly, and you'd have to design your airplane so you had a hard point to tow it. The problem is when you let go, because having let go, I've still need all that power because I'm trying to climb away quickly. I'm trying to get to an altitude which is safe enough to go around if I have an engine failure. And you know, this isn't the military, and we don't have the same risk profiles there. So you could do it theoretically. Whether you would ever get through any safety regulations, I don't know. And I suspect it adds a huge layer of complexity that we probably don't need.
Question from Peter. What are the greenhouse gas implications of ammonia leakage in the atmosphere?
Well, I was going to say they mostly come through the medium of NOx. NOx is a big problem. NOx is a big problem at the moment with existing aircraft, and fuel cells will reduce that. So I think that whatever you've got, we're going to get it better.
There's another question here, this time from Barry McMullen. Can you comment on the non-CO2 climate forcing from conventional fuel aircraft and how that compares with NH3 aircraft? Combustion, fuel cell may be different.
Really good. It's a really good question. So there's a whole lot of misunderstanding in this particular space. And the reason for the misunderstanding is that a lot of the analyses has presented the RFI, the radiative forcing index, of the various atmospheric disturbances that go on. So contrails, anthropogenically induced cirrus clouds, NOx, and so on. The problem with RFI is that it really cannot be translated across into the global warming potential because these are very, very short-lived. You know, ice crystals in the atmosphere have a lifetime measured in hours. CO2 in the atmosphere has a lifetime measured in thousands of years. So you have to be careful how you interpret the data. However, if you go down the fuel cell route, well, no, let me go back. Any fuel that contains carbon that you burn almost inevitably produces tiny particles of soot. And it is those tiny, tiny microscopic particles of soot which act as the nucleation sites for ice crystals. And contrails and anthropogenically induced cirrus, AICs, are the principal non-CO2 forcing component. The moment you go to a nitrogen-based carrier, you take out the carbon. So none of that happens at all, right? That's the biggest single piece. NOx we've talked about. Sulfur and sulfates, well, there aren't any there. Interestingly enough, a combustion engine does burn a little bit of atmospheric methane, so you get a bit of a credit there. And if we go to fuel cells, you wouldn't be doing that. And that's about it, really. Basically, it's a much better situation moving away from a carbon-based fuel.
A question here from Doug. Some photos you see of electric aircraft have a large number of small propellers. Why is that? Aren't large engines / propellers more weight efficient?
Okay, a very interesting question. In gas turbines, size matters. The bigger it is, the more efficient you can make it. For electric motors, that is no longer true. So for an electric motor, I've seen dyno tests recently on a company that I'm involved with efficiencies in excess of 98.5%. And you'll get that efficiency at every range from 100 kilowatts to 10 megawatts. So I don't believe there is an efficiency issue there. As far as the propellers are concerned, you have the great advantage with smaller propellers that you're not running at the speed of sound at the tip when you're running at reasonably high RPM. So propellers don't gain from being bigger and bigger and bigger. What you gain from having lots of small propellers is you've got airflow over the wing. So you've got a lot less, you haven't got this great big spiral flowing over the wing. You have more continuous airflow. And because you've got a lot of airflow over the wing, effectively, even at 0 ground speed, you've got some airspeed. So a lot of the small planes you've seen allow much better short field performance and slow speed performance because the propellers are inducing flow over the wing.
Thank you. A question from Don. What is the energy efficiency of making ammonia? That is, how much must you put in per amount of usable energy in the aircraft?
Okay, I'm going to be heretical and say it really doesn't matter. And the reason it really doesn't matter is that we're not short of energy. The Sahara is full of it. 5% of Western Australia covered in solar panels would produce as much energy as the current global oil and gas industry. It is purely and simply, in that case, a matter of cost. And so in the cost modeling that I alluded to there, what I did is I built an ammonia plant in a sunny place, Western Australia or the Namib Desert, and we built the solar field to power it as part and parcel of the plant. So energy efficiency just doesn't come into it, the sunlight to solar conversion will be only 25 to 30% efficient. It really doesn't matter. We're not short of energy. What we're short of is the right energy in the right place at the right time.
Thank you. A question from Anonymous. How does kerosene compare in terms of toxicity? Presumably it cannot be completely safe.
No, but it's pretty damn safe. I mean, you'd have to drink it, wouldn't you? And you're not going to do that. I don't think there are any particular problems with kerosene spillage and things like that in terms of short-term toxicity to people. The problem with kerosene is fire. It's got a very low ignition point. It burns too easily.
A question now from James. Thanks very much, Mike. Could you say a bit more about the non-CO2 effects of using ammonia and how to mitigate these?
Okay, so well, this comes back to the non-CO2 effects of using ammonia are fundamentally nil to the extent that you're going to nitrogen, 78% of the atmosphere, and water. The only problems with ammonia come if you burn it and you produce NOx, which you don't want to do. But we know how to, in principle at least, and certainly in the laboratory, we know how to control that. And the problem of disturbing the global nitrogen cycle from ammonia leakage. And that's unlikely to be material, except to the extent that we have long-term persistent leakages. And we won't get those because, as I say, ammonia is much, much easier to detect than hydrogen or natural gas.
A question now from Stephen.
My favorite question.
Can you refuel in flight?
I took that slide out because it's too controversial. Of course you can. So the first mid-air refueling was done in 1923. And I've got a picture of it. And there are two biplanes, and one's let a hose out with a funnel, with a nozzle, and the other chap's got a funnel and he's refilling his aeroplane in the air. We've refueled aeroplanes in the military for 40, 50 years now, and there has only in that time been one crash caused by the refueling process. The President of the United States in Air Force One routinely mid-air refuels. There you've got a 747 being refueled by the military. This is not at all difficult. I've got a drone, it's a few £100 worth of drone, and I can position it within 100 millimeters in three-dimensional space just by pressing a button. Of course we can. Whether I can persuade the world that this is a sensible thing to do, I doubt. But your questioner is absolutely, Stephen is absolutely right. Of course you can refuel in flight, and that is where we're going to solve the long-term problems.
A question now from David Lucas. Is there going to be enough renewable electricity to sustain the level of flying we have at present? We will need a huge amount of electricity to power our heat pumps when we are no longer burning gas and oil?
Yes, and you can have 3 orders of magnitude more. If you look at solar, as I said, 5% of Western Australia could provide as much energy as the entire global oil industry. And we haven't looked at the other 95%, or Queensland, or New South Wales, or South Australia, or the Sahara, or the Gulf, or China, or India. Yes, more than enough. We will never, ever, ever run out of solar energy. That's the one thing we can be certain of.
A question now from Alex. Thank you very much. That was a fantastic presentation. Would there be any issues in relation to flight ceilings?
The flight ceilings. Not insoluble ones. As you get higher, you will have to pressurize air into a fuel cell. No question about that. There is no fundamental problem with that. It's just a matter of the parasitic load required. It's engineering. I don't think there's a fundamental problem. There's nothing that says you can't go above. Why are there not more solar farms in the Sahara? Can I take that one?
Yes.
Okay, I mean, there's a really interesting bit of history here. There was a project called Desertec 10, 12 years ago, something like that, which wanted to build solar power in North Africa and ship it to Europe. And the Italians wanted the wire, and the Spaniards wanted the wire, and the French wouldn't have the wire crossing the Pyrenees because it would undermine their nuclear industry. And there was a whole raft of politics. And anyway, who would have wanted to put it into Libya? And so it didn't happen, quite rightly. However, the problem with solar electricity is that it's at the wrong time and the wrong place. What you need to do is to find a way of turning solar electricity into something you can move cheaply, easily to somewhere else. And the beauty of ammonia in this context is that that's what you can do. So I don't know if any of the people on the call saw a huge project in northwestern Australia recently. It was originally going to be a 26 gigawatt solar and wind farm producing electricity, which was going to be shipped at megavolts through to Singapore. And that was abandoned because I think, as much as anything else, well, earthquakes in particular, but the politics of crossing Indonesia, and everyone on the route now has a monopoly over what you can do. And then you've only got one buyer at the other end anyway. And they have converted the project to run on ammonia. So now the world's biggest ammonia project is going to be a green ammonia project done in the deserts of northwestern Australia. Saudi has committed to building the NEOM project in the Gulf, actually just off on the Red Sea, and it's going to be a huge new sustainable city, all totally sustainable, no fossil power at all, with a massive solar ammonia facility there. So the reason it hasn't happened in the past is that we haven't had an easy way of taking the energy out to transport it around the world. Developments in the ammonia space are going to totally transform this.
Another question from Anonymous. Hydrogen production is likely to be widespread 5 to 10 years from now to deal with our increase in SN/SP electricity. How many years will ammonia be used in the aviation industry given this?
I'm not sure that I understand the question, because ammonia will outcompete hydrogen. Ammonia made in sunny places will be as cheap as hydrogen made here. And it will be much, much cheaper to store and much, much cheaper to move around. And so I just don't see hydrogen making it into aviation when it doesn't offer any advantages over ammonia.
Could you see offshore wind power being used as ammonia energy source?
Absolutely. If you take the Dogger Bank wind project just off the coast of England, I think 30 to 40% of the total project costs are the costs of getting the electricity ashore. Now, you could do two things. You could make hydrogen with it, or you could make ammonia with it. Hydrogen, you would have to ship probably by pipeline, but there's no principal reason why you couldn't take it by pipe onshore, or you could make ammonia. And it's really going to depend on the relative values of those two commodities and the costs of making them. There are some big developments ongoing in electrochemistry, which will allow us to bypass Haber-Bosch completely and go straight from air and water and electricity to ammonia. Though at the moment, the technology has it's very high Faradaic efficiency, but quite a low overall electrical efficiency because the excess voltage needed to dehydrogenate the lithium is high. But watch this space. So it's quite possible. Just at the moment, I think it's more likely to be hydrogen.
Thanks, Mike, for an excellent presentation and for handling the question so well. I will now like to invite Seamus Doyle from the Ireland Network to propose the vote of thanks. Seamus.
Thank you, Chris, and good evening, Mike, and ladies and gentlemen. It gives me very great pleasure indeed to propose this vote of thanks to Mike. This subject is very topical and a very important issue. Climate change is a major issue for the entire world. Internationally, we have global targets for carbon neutral living, but these targets are for 2050. And we know only too well that if it were not for the last minute, nothing would get done. So this much needed action may be some time away. And Mike is not waiting. He, as Aidan said earlier, he founded Climate Care, the world's first carbon trading business. He was advisor in the Maldives, where his brief was to create a fully renewable economy. He is a researcher and an investor in the transition to a negative carbon economy. So we are fortunate indeed to have such an expert address us this evening. Mike has, I think, held our attention and provided us with a well-constructed and well-delivered paper. His work on ammonia is fascinating and a breath of hope for the future of energy storage. And it's not pipe dream. For those interested in car racing, Formula E is already an established mark as Formula One electric racing. Electric air racing is about to start, I understand. So, you know, the use of electricity in transportation and in aviation is already happening. He has, I think, presented a very balanced argument. He's considered the alternatives, and he has considered the various ways that ammonia can be used, as well as the problems. Mike, on behalf of the IET and all of us participating this evening, thank you for sharing your expertise and your vision for the future of energy storage. A most interesting and informative lecture. Thank you. Over to you, Chris.
Aidan, could you sum up?
Thanks very much for that, Seamus. I have to admit at this point, maybe admit's the wrong word. I did start off at Rolls-Royce as a graduate apprentice, so I was fascinated by the talk. But that was more than 25 years ago, so I don't recall ammonia being mentioned at the time, and it's kind of in my past. But I can see why they wouldn't be keen for you to come romping in and steal the show at this stage. But the thing that did strike me during the course of the presentation was that if we look to the skies at the minute, one of the things that I do notice is that there is very few planes flying. And so apart from COVID and the climate change and things like the 737 MAX debacle, there's definitely challenges there to the Boeing Airbus duopoly. And it's the sort of crisis potentially which could be a catalyst for change to a greener future as we hopefully start traveling again in the future. And So I'd also like to add my thanks, and also thanks to everyone for attending this evening. What has been a fascinating talk. So, and I'll pass it on to Chris now.
Thanks again, Mike, for an excellent presentation, and thanks to all who attended this evening's webinar. I look forward to seeing you all again at our next one. Goodbye.